Alrighty, so we'll begin our study of energy and work by a little handout here on energy. And I mean, the first few things in the outcomes there: define work as the product of the space that's going to come up, determine work, basically describe work as the transfer energy. We're going to be sort of taking care of some of this introductory stuff to begin with. Is that thing on back there? Dan, is the speaker on? Oh, I got to turn this on. Is that better now? Okay. All right, so energy is the most central concept that underlies all of science. Without reading ahead, what is energy? Hard to define, isn't it? And for me as well, and for scientists as well, what is energy? Surprisingly, the idea of energy was was unknown to Isaac Newton, and its existence was still being debated in the 1850s. So it's a relatively new concept in sort of the science world. The concept of energy is relatively new, and today we find it ingrained not only in all branches of science, but also in nearly every aspect of human society. We're all quite familiar with it. Energy comes to us in the form from the sun in the form of sunlight. It is in the food we eat, and it sustains life. Energy may be the most familiar concept in science. Everyone sort of kind of gets it, yet it is one of the most difficult to define, oddly enough. Persons, places, things have energy, but we observe energy only when something is happening. Where is my highlighter? Doohickey thing. We observe energy only when something is happening. Only when energy is being transformed from one thing to another. Allow me to demonstrate. Classic. Tennis ball. How many things do I use tennis balls to describe? I pull it out probably once a month. Oh yeah, so I hold the tennis ball like that. Does it have energy? It has. Oh, well said, Joey. It potentially has energy. I think there was a little pun there. It does. It has potential energy. How come? Because of its. Yeah, okay, because of its mass, because of its gravity, because of its position, right? It's got energy because I'm holding it up in the air, and if I were to drop it, that potential energy would transform into kinetic energy via the law of conservation of energy, right? This is what I was explaining to Justin last night. I was saying how the very first thing in a roller coaster, what's the first thing in a roller coaster? Always. They drag you up to the top of a great big hill, and then they let you go. And every hill after that is always a little bit smaller. Have you noticed that? The big hill's right at the start, right? And then it drops down, and then it goes up again. But that second hill is never as high as the first one. How come? Wouldn't make it because it's losing some energy due to air resistance, right? Okay, and the whole idea is based on this, really. So it's kind of, almost like cosmic that I got this call out of nowhere. And it said, lead momentum, do work energy unit. So I listened to the voices in my head, or in my phone. We'll begin our study of energy by observing a related concept, that being work. Work is a little bit easier, if you'll pardon the expression, to work with. The last chapter showed that changes in an object's motion are both related to force and to how long the force acts. How long meant time. The quantity force multiplied by time is called impulse. That's a momentum concept. We'll get to that. But how long need not always mean time. It can mean distance as well. And oddly enough, here in Canada, if you're driving to Eyebrow Lake, Saskatchewan, someone will say, how far is it? Invariably, we are told the answer in hours. Have you noticed that? It's a Canadian thing. It's Canadian.
I actually no one says hours.
Pardon me?
All the Americans I actually
Yeah.
say miles.
Say miles, or yeah. So we.
Starts between the metric generation and the period.
Well, maybe. I don't know. Or maybe it's just because everywhere is so far away in Canada that you have to measure it in the actual time it takes you to get there. I don't know. Yes. That's interesting that you noticed that too, Joe. When we consider the quantity force times distance, we are talking about a wholly different quantity, a quantity called work. So there, I've defined work for you. It's what? Force multiplied by distance. We do work when we lift the load against the Earth's gravity. The heavier the load or the higher we lift the load, the more work is done. Two things enter into every case where work is done. There must be a force, and there must be the movement of something by that force. Am I doing work right now?
Yes.
By definition, there must be the exertion of a force. Check. The movement of something by that force. Not check. I am doing no work. I can stand here all week. No work. Will I get tired of doing this? Oh yeah, it won't take all week. It'll take about 10 minutes before I'm tired of doing this. No work done. If I do this, am I doing work? Doing a lot of work. And if it was a heavier tennis ball, even more so. There must be a distance. Must be movement. There must be a distance. You have to be able to measure some distance for there to be work. Look at the simplest case in which the force is constant and the motion takes place in a straight line in the direction of the force. Then the work done on an object by an applied force is defined as the product of the force and the distance through which the object is moved. In shorter form, work equals force times distance. There's the formula you're going to need. Jake has a question.
So how come resisting gravity doesn't count as work?
Because there's no distance. Are you burning energy? Yes. If I stand there, I will get tired, and I guess if you could somehow measure my energy in my body, it would decrease. So, conservation of energy says energy must be conserved. Where does the energy go? In the form of heat. I'm standing here, burning off my morning Cheerios, generating heat, body heat. Right? So energy is conserved. Does that help? Randy? Entropy? No. What's entropy? The measurement of randomness.
Oh.
It sounds like there could be a lot of uncertainty in the measurement of randomness. Almost. If you lift loads, two loads, one story up, you do twice as much work as you do in lifting one load, because the force needed to lift twice the weight is twice as great. Similarly, if you lift a load 2 stories instead of 1 story, you do twice as much work because the distance is twice as much. Note that the definition of work involves both a force and a distance. A weightlifter who holds a barbell that weighs 1,000 newtons overhead does no work, as I've indicated. He may get really tired doing so, but if the barbell is not moved by the force he exerts, he does no work on the barbell. Work may be done on the muscles by stretching and contracting, which is force times distance on a biological scale, but this work is not done on the barbell. So I sort of fudged a little bit when I said, am I doing any work? I'm not doing any work on the ball, the tennis ball, but I am doing work inside my arm, right? I'm doing my muscles are contracting very microscopically. Okay? So I guess there is work being done, but that's what's generating the heat. Lifting the barbell, however, is a different story. When the weightlifter raises the barbell from the floor, he is doing work. Work generally falls into 2 categories. One of these is work done to change the speed of something. This kind of work is done to bring an automobile either up to speed or slowing it down. Like when you put your foot on the gas, you're converting energy in your gas tank to, well, mechanical, to which converts to kinetic, right? The other category of work is the work done against another force. When an archer stretches her bowstring, she is doing work against the elastic force of the bow. When the ram of a pile driver is raised, it's exerted against the force of gravity. When you do push-ups, you do work against your own weight. You do work on something when you force it to move against the influence of an opposing force, like gravity. When you run up the stairs because you're so excited to come to physics class, are you doing work? Yes, the distance is the height of the stairs. It's the mass. What's the force? Force of gravity on you, right? You have to oppose gravity. And if you do it really quick, do you do more work or less work? Ah, someone said the same. Why do you say the same, Dallas? Excellent, by the way. No, I don't want to close it. Why did you say the same amount of work? That was you, Dallas, wasn't it? You're right, by the way. Just got a feeling?
You listen to me.
It's the same distance, and the force is also the same. Absolutely, you're absolutely right. Nail on the head. The work done is the force times the distance. The force is the same, and so is the distance. So what's different when you run up the stairs really quick as opposed to dragging your butt up the stairs? A concept I haven't talked about yet, by the way. Although it is in grade 9 science, oddly enough, in the electricity unit. Did you ever have to go and look at your hydrometer at home? No? We didn't have to do that, grade 9 science? And what's it measured in on your meter at home? And it's kilowatt hours is what it is on your power meter, right? But you're right, watts is the unit of power. And so when you run up the stairs really quick, we're talking about power. So what we're going to do is we're going to find out who has the most power in the room. Who can get themselves up the stairs, not just the quickest, but also, right? If you're a bigger person, right, you have a bigger mass, which means you have to go become a bigger force. So bigger people, like if, for example, a small person and a large person, right, if we brought in one of the daycare kids and they ran up the stairs in the same amount of time as me, who's got more power? I do. How come? I have to provide a greater amount of force. Same distance, same amount of time, right? So power is not just about the fastest, it's who's the biggest and the fastest. All sorts of pre-teaching going on here. A unit of measurement for work combines the unit of force, the Newton, with a unit of distance, meter. The unit of work is the Newton meter, which is weird, so we came up with a new one called the joule. A joule of work rhymes with pool. When you have 1,000 joules, then you have a kilojoule. Have you ever seen that unit before? Kilojoules. Where would you see it? Yeah, I think it is an electricity unit, right? You're right. I think so. 1 joule, symbol J, of work is done when a force of 1 Newton is exerted over a distance of 1 meter. It's one of those predefined units that humans came up with, right? So it's 1 Newton meter, as in lifting an apple over your head, or basically tennis ball. When I lift the tennis ball 1 meter, I'm doing 1 measly joule of work. For larger values, you speak of kilojoules, which are 1,000 joules, or megajoules, millions of joules. A weightlifter does work on the order of kilojoules. When you go to the fitness center and you lift weights, you're doing kilojoules of work. The energy released by 1 kilogram of fuel is on the order of megajoules. So a joule is a very tiny, tiny amount of work. You are all, I'm sure, familiar with the idea of calories, right? Calories in food content. Did you know that technically, and this is not on the sheet here, but when you talk about calories, like say, what would be, anyone have anything to eat? All I see is water. Usually there's someone in the room that's got something. Always a wrapper or some other known that's big into the recycling. Excellent. Snapple. I knew there was a reason why we had these in school. Okay, so it says here, 160 calories. What does that mean? Yeah, 1 gram of water, 1 degree Celsius. How much energy is that? Really? A little teeny, itsy bitsy teeny weeny gram of water by a measly 1 degree Celsius?
That's the calorie.
That's like nothing. Like no energy at all. And there's only 160 of these in here? They're fooling you, folks. Because the definition of a calorie, and Brandon is 100% right in her definition, that is the definition of a small c calorie. Okay? And when I see 160 calories on here, 160, do you notice the difference? It's a big C. They're fooling you because 160 calories, big C, is technically 160,000 calories. The big C is kilocalories. No one's ever going to eat a piece of cake if they know that there's 500,000 calories in there. I got a little excited and sprayed Snapple all over the table. So the food industry, I don't really know, I'm making this up now. The food industry has come up with the big C calorie, which is technically a kilocal. Does that make sense?
But don't you also burn like 230,000 calories for every hour?
Absolutely, yeah. I mean, it's when you see that on there, right? I mean, it makes sense to me, right? Like they're not going to put actual calories. Some food products actually show it in joules. Very, very few. Over the next couple weeks, look for just look for joules, would you? I know of one food product that has it on there. That's the only one I've ever seen it on. But I may be missing something.
What is it?
Can't say. Because then you'll go and you'll find it, right? I'll just tell you. Vector cereal. Vector cereal and Vector bars are the only food that I've ever seen that has it measured in joules. Joules is technically more scientific. Although the calorie is like a science term. Food calories is kind of, but anyways. So have a look for joules of energy on your food product. Again, it'll be listed in kilojoules because the joule of energy is not very much. And there is a conversion factor between calories and joules. Okay, let's talk about power. Definition of work says nothing about how long it takes you to do work. When carrying a load up some stairs, you do the same amount of work whether you walk or run up the stairs, as Dallas correctly indicated. So why are you more tired after running upstairs in a few seconds than after walking upstairs in a few minutes? To understand this difference, we need to talk about how fast work is done. Power. Power is how fast the work is done. Power is the rate at which work is done. It equals the amount of work done divided by the amount of time during which the work is done. Why is there a big space there? You have something? Oh, you have formulas and I don't. Power equals work over time. How many people have a snowblower at home? How many horses does it run, you know?
No, sure. I always use it.
He doesn't let you run it, eh?
Oh, he loves that thing more than me.
Oh yeah, he loves a snowblower. Okay, well. Okay, who else has one that maybe knows how many horses it has? Anyone? I saw a couple. Jake, does I see a hand here, or Chris? No idea how many horses it is? Hey? 4-horse snowblower. Okay.
Plow truck that has a few hundred horses.
Okay. So yeah, we're talking. Yeah, no, I'm just talking like the regular clean your driveway out kind of horse or snowblower, right? So you might get like a 4-horsepower snowblower, and you might have, let's say, an 8-horsepower snowblower. What's the difference?
Well,
We'll
be able to move horse.
We'll
have easier time.
Will the little 4-horsepower one do the job? Yeah. Will it? Not as fast. Power is measured in horsepower in the old world, right? If you look at a small horse snowblower, you'll see that the swath, I guess you could call it, the deck, the width that it cuts is just tiny, like this, right? And if it's got more horsepower, it's got bigger deck, bigger swath, because it does the same work in less time. It's got more power. Now, we get like 4 feet of snow like Buffalo got, like that, crazy storm a few weeks ago, right? Will my dinky little 2-horsepower snowblower cut it? It ain't gonna work at all, right? I'd have to be taking off like this much snow at a time. It's very thin, right? So yeah, so when you measure your horsepower of your engine, same thing if you've got like a quad or a motorbike or whatever. In fact, your car, if you look inside your car door, there should be a rating for how much horsepower it has. It might also be measured in, anyone know? kilowatts. No, I don't want horses. That's old-fashioned. Yeah, watts. An engine of great power can do work rapidly. An automobile engine with twice the power of another does not necessarily produce twice as much work or go twice as fast as a less powerful engine. Twice the power means it will do the same amount of work in half the time. Twice the power means that it will do the same amount of work in half the time. There's my phone. The main advantage of a powerful automobile engine is its acceleration. It can get the automobile up to a given speed in less time than the less powerful engine. So if I get myself into a brand new 2014 Mustang, Joey gets himself into a brand new 2014, no, I'm thinking something a little smart car. Sorry. You can have the Mustang, I'll take the smart car. Joe, can we both get up to 100 kilometers an hour? Sure. It's just that Joey gets there a whole lot faster. He's in the Mustang. He's got a lot of horses under the engine. Meanwhile, I've got a little pony. Right? For me? Well, okay. Technical Mr. Carr. The basic analogy is the same. We can look at power this way. A liter of gasoline can do a specified amount of work, but the power produced when we burn it can be any amount, depending on how fast it is burned. The liter may produce 50 units of power for half an hour in an automobile, or 90,000 units of power for 1 second in a jet aircraft. Basically, the jet fuel is just designed to burn faster. Same amount of work. The unit of power is the joule per second, also known as the watt, in honor of James Watt, the 18th century developer of the steam engine. I love throwing those little history things in there for you, okay? If you're ever on, Jeopardy, you'll remember that, James Watt, unit of power. 1 watt of power is expended when 1 joule of work is done in 1 second. A kilowatt equals 1,000 watts. A megawatt equals 1,000,000 watts. In the United States, we customarily rate engines in units of horsepower and electricity in kilowatts, but either could be used. In the metric system of units, cars are rated in kilowatts. And in fact, in Canada, I believe cars rated in kilowatts. So have a look at your car door. It should be there, your engine rating. 1 horsepower is about the same as 0.75 kilowatts. So an engine rated at 134 horses is a 100 kilowatt engine. I think it's 705 watts per horsepower. It was technically one time it was how much work a horse could do. 1,000 horsepower was how much work a horse could do in 1,000 hours or something. It had to do with raising water in a well. Every horse is different, right? So it's really not a very good definition. The 3 main engines of the Space Shuttle, which no longer run, by the way, can develop 33,000 watts of power when fuel is burned at the enormous rate of 3,400 kilograms. That's what that should read. 3,400 kilograms per. It's like emptying an average swimming pool in 20 seconds. Imagine the rec center pool gone in 20 seconds. That's how fast the fuel goes. That's a lot of power. When work is done by an archer in drawing the bow, and I mean like a pencil, the bent bow has the ability of being able to do work on the arrow. When work is done to raise the heavy ram of the driver, the ram acquires the property of being able to do work on an object beneath it when it falls. When work is done to wind a spring mechanism, the spring acquires the ability to do work on various gears to run a clock, ring a bell, or sound an alarm. In each case, something has been acquired, right? Like when I wind up a spring, what does the spring now possess? Energy. This something which is given to the object enables the object, because when I release the spring, it'll fling a ball through the air, or what have you. This something may be a compression of atoms in the material of an object. It could be a physical separation of attracting bodies. It could be a rearrangement of electric charges in the molecule of a substance, like a battery. This something that enables an object to do work is called energy. There it is. There's your fancy science definition for energy. Something that enables an object to do work. Could you definition than that? I don't think so. Google it up, see what you get. You're not going to get much better. It's really, really hard to define. Like work, energy is measured in joules. It appears in many forms, which may be discussed in the chapters. For now, we'll focus on mechanical energy, the energy due to the position of the movement of something. Mechanical energy in the form of either potential energy or kinetic energy. So work is almost like the unleashing of energy, right? It's the converting of energy to some, shall we say, useful, some kind of movement. Potential energy. The energy is called potential. As the potential for call walking reservoirs of energy, because at any given moment you run away or lift a bus or not do anything. Then you wouldn't be converting that potential energy, right? You have a lot of potential, you guys. Potential energy. So at grad, when the guest speakers are talking about your potential, right now Mr. Bennett's thinking, yeah, they're just walking around with all this food in them full of going. Hey? Kilojoules, yeah, well, there's, right? Kilojoules, kilocalories. We all have. That's how much you ate for breakfast. A stretched or bow, for example, or spring, the potential for doing work. When a bow is drawn, energy is back able of doing. Potential energy. This energy is potential energy. The can of a Snapple possesses potential energies from fossil fuels. Upward force height h is given by